Today we'll talk about identifying quadratic functions and how we can determine if they have a maximum or minimum. And of course, we should be able to graph them given its domain and range. Let's get you started. Right now we have what you call here the graph of a quadratic function, which we actually call as a parabola. Okay, and it is resembling a U-shaped graph, but notice how we have arrowheads at the end. This means that the graph continues infinitely. So for example, notice that this function opens upward, okay, represented by y equals x squared. And so your graph shows that these sides are infinitely going to the left and to the right. However, notice how the y values are only the values that are going upward. Okay, and so when you talk about the graph of a quadratic function, which is called a parabola, we also have what you remember we called as the standard form of a quadratic function. So this is the function in the standard form, meaning it's arranged from the highest degree to the lowest, where the a value cannot equal 0. So now we ask ourselves, why can't a be 0? So think about this. If a were 0, let's assign specific values. Say a were 0, right? 0x squared, maybe a 3x here, and a 5. Think about this. What happens if you multiply any variable, any value by 0, right? It just ends up as 0, so it's gone. All you're left with at this example, at least, is 3x plus 5. And when you think about it, will that equation resemble a quadratic function? No, it doesn't, because now it's actually a linear function. Okay, so that's why a can never be 0. Otherwise, it's not a quadratic function. Let's go forward. Okay, so now we know the standard form and the graph of a quadratic function. Let's go further into discussing how we can identify whether a given set of points or an equation can be determined to be a quadratic function. Let's take a look. If you were given a set of points, okay, in a table form or just coordinates, how can you tell it is a quadratic function? The first thing you can try to do is to graph it. Plot your points, connect it with a nice smooth line or curve, and you should be able to see whether it produces our parabola. On the other hand, you can also attempt and do the following. You need to check that the changes in the x values are constant. Let's look at this example. Notice how the x values are increasing by 1, okay? But at the same time, we look for what we call the second differences. Okay, this is so special because what are second differences? Okay, let's have a discussion about that. When you look at the x values, there should be a constant change. Now we look at the y values. What we refer to as the differences is this. From a 0 to a 1, we changed by 1. From 1 to 4, we added 3. From 4 to 9, and 9 to 16, and so on. Now, these numbers that we found, 1, 3, 5, and 7, are what we call the first differences. Okay, but for it to be a quadratic function, we're looking for the second differences. Okay, so let's see, what does that really mean? Because you've found the first differences, to find the second differences, you look for the difference from this value to the next one. In this case, it's a 2, and it appears to be consistently 2. So we say, okay, the given set of points actually represents a quadratic function because there is a constant second difference. And that's what it means to have a second difference, a constant second difference. Okay, so let's try the 3 examples right below. Let's start with a table. So similarly, you check for the changes in the x values. This is constantly changing by 2. Okay, now you need to confirm if the other sets or pairs of points also increase by 2 constantly. It appears to be so. Okay, now let's check the y values. What are we looking for again? Yep, to produce constant second differences. Okay, let's look for the first difference. The first difference is from 8 to 2, we took away 6. From 2 to 0, you take away 2. Okay, this time we're adding 2 and adding 6. Okay, so obviously it's not a linear function because the first differences are not the same. So now let's check for the second differences. From -6 to -2, what was the difference? We're adding 4. From -2 to 2, we're also adding 4. And let's confirm if the last one is as well. And yes, we keep on adding a second difference, which is a constant value of 4. So therefore, we say that yes, this is a quadratic function. This represents a quadratic function. So that's how you can tell that a set of points is representative of a quadratic, and my pen is not writing, quadratic function. All right, so moving on. Now we've checked for a table and set of points. Now, how do we tell if an equation represents a quadratic function? Okay, so go back to what we just discussed in the previous slide. We said that the equation always needs to be in standard form. So you can tell that the highest degree is 2 and that it's arranged specifically from the highest to the lowest degree. All right, so let's confirm. In this case, we have the bx term and the c term. My question is, where's the ax squared term, right? Okay, because it's missing, we say that this is actually not a quadratic function because, right, when you are looking for the value of a here is actually equal to, correct, 0, because you can't see it. So therefore, a is 0. So we say, okay, this is not a quadratic equation. Okay, so let's look at the third equation. All right, so start over. Is it in standard form yet? No, it isn't. So rearrange your equation. So I'm going to go ahead and rearrange this, moving 3x squared, making it negative, like so, minus 4. Okay, so remember, in standard form, you should have the ax squared term, the most important. The bx and the c can exist or not exist. It's not a problem, as long as the a value is there. All right, so because we can see that there is an a value of -3, we say that this is a quadratic function because it can be written down in the standard form. Quadratic function because it can be expressed in the standard form of the equation. All right, so right now you know what the graph looks like. You are able to tell whether an equation and a set of points represent a quadratic function. We'll move on to practicing. Now you can pause this video at this time and give yourself some time to practice and answer the questions. Okay, so for the first one, I have a set of points and it appears, okay, that this is actually a quadratic function because there is a constant second difference. Now, what does that mean? Let's look at this table that I've produced. If we were to list down the sets of points, there will be a constant difference in the x values. Similarly, for the y values, you're looking for your second differences. So take a look. We actually produced a difference, a constant difference of 2. And that's their explanation behind saying that it is in fact a quadratic function. Meanwhile, on the second example, it is not in standard form, so you had to rearrange it like so. And once we've done that, okay, we've noticed that the a value exists. So we say, okay, this given is actually a quadratic equation because it can be expressed in the standard form where a is not 0. Good job on that one. Let's move on. All right, so in this example, this time, we will have a discussion about graphing your quadratic functions. Now, some of you may have access to a graphing calculator or Desmos or the TI program that I've shared with you previously. Or if you prefer to graph manually, that's not a problem. But these are the expectations for graphing quadratic functions or equations, all right? You must choose any 5 points. And once you have these 5 points, you can connect them. The objective is to produce what resembles a parabola. Okay, otherwise you might want to choose a different set of points or add a few more points so you can see a curve. It needs to show a curve that resembles a parabola. Let's take a look at the first example on the left-hand side. Notice how we have 2x squared, okay? In order to graph this, some of you will use your calculators to graph it. Otherwise, here's how you can do it manually. You must choose, remember to choose your own sets of x values. It doesn't matter what values you use, but for sure, the most commonly used values are from -2 to 2. Okay? All right, so how do we actually get the y values? You choose the x values, but how would you find the y values? And this is how you do them. All right, so now we've chosen your x values. Basically, we're going to plug it in. So we say y equal to 2. Okay, notice it's a -2. So I really encourage you to use a parentheses. We're going to square that. You go 2 multiplied by 4, and that's how we get the 8. In the same manner, you can find the other y values with those steps. So really, one of the points is -2 comma 8, which we can plot over here. And in the same manner, you have -1, 2, and so on and so forth. Once you've plotted the points, notice how you can connect them. Nice and smooth. Okay, so that's how you can determine whether the sets of points will represent a quadratic function. On the other hand, what if you had y equal to -2x squared? Okay, in the same manner, you choose any 5 points. Okay, mostly you want to select values that are consistent and consecutive, and in doing so, we produce the following y values. Now we have our coordinate points. Let's plot those 5 points and connect them with a nice curve, thus showing us your parabola. Okay, so hopefully you have those options. You can use whichever one you're more comfortable to apply, whether you use a graphing tool or manually graphing these points. Okay, all right, let's go forward. Let's have you practice on the following. Again, you can pause this video right now and go ahead and try to graph the functions. See if you can produce a similar graph. Okay, on the left-hand side, you have an x squared plus 2. Let's see what points I used. In this case, I've chosen to use values from -3 to 3. Again, you only need 5. I just went extra just so we have a clearer visual. Okay, so observe how the graph looks like right now. Okay, it is very interesting. Take a look at this. Your parabola has a graph that opens upward. Okay, there is this lowest point right here, and it just keeps going up infinitely. And so you can go ahead and check at -2, 6. Let's find -2, 6. This is by ones. 1, 2. This is a 6 right here. That's the point that we produced, and the others lie on the same graph. On the other hand, if we have a -3x squared plus 1, I used values from -3 to 3 once again and produced the following y values. And in doing so, I produced a graph that resembles this. This time the graph opens downward with the highest point up here, and all the values keep decreasing, at least for the y values. Okay, so hopefully you were able to check that. Let's bring you forward. Okay, so now we can establish that we're able to graph, but now how do we confirm? How do we confirm whether the graph needs to open upward or downward? Those are the only two directions anyway, but how do you tell specifically? Okay, so there is a specific rule, and there's only two. It opens up if and when the a value is greater than 0, and it opens downward if the a value is less than 0. Remember, you want your equation to be in standard form all the time. All right, let's take a look at the following. On the left-hand side, you have y equal to 4x squared. Let's determine whether this graph opens up or down without actually graphing them. Okay, so graphing at this point should just be a tool for you to check your work. So 4x squared, what would the a value be in this example? Okay, correct, a is equal to 4. And because a is 4, a should be greater than 4 or a greater than 0, therefore the graph opens upward. So we say, okay, the graph opens upward. And if you try graphing it On your calculator, it would resemble something similar to this. Okay. On the other hand, let's look at the second one. This example that we're given is not yet in standard form, so let's isolate y, making sure that we update the sign. So moving 2x squared creates a negative 2x squared plus 5. If so, what is the a value this time? Right? Okay, so it is negative 2. And because it is negative 2, it is less than 0. So we say that this actually opens downward. Okay, so your graph would resemble a parabola that would look like this. All right, so that's how you can tell whether a graph opens up or down. In the next part, let's give you an opportunity to pause the video right now and practice on determining whether the functions that you're given opens up or down. Okay, and the first one, check that the equation is in standard form. If it is, what is the value of a? In this case, it is negative 4, so we say that because the value of a is less than 0, the parabola actually opens downward. On the other hand, our second example is not in standard form, so how can we rearrange that? Okay, so let's take a look. You must make sure to write it in standard form, and once you do, it would look something like this. Now, what is the value of a that we know? Yep, it is positive 5. And because it is positive 5, we say that the a value is greater than 0. Therefore, the parabola actually opens upward. Okay, good job on that one. You now know how to graph, how to tell if the graph opens up or down. Now we'll bring you to the part where you're actually looking at what you call a minimum and maximum point, as well as the vertex. Remember how we kept mentioning that there is the highest point and the lowest point. Those are what you would call your minimum and maximum values. All right, so how do you tell when it's a minimum or when it's a maximum? First of all, you need to identify which way the graph opens. If the graph opens upward, normally there is a lowest point, and that lowest point will represent your minimum point, otherwise known as your vertex. It's the tip of your parabola, and it actually is the middle of the whole graph. It's so symmetrical, it's so beautiful, right? In the same manner, if the graph opens downward this time, you have the highest point because all the y values just keep decreasing all the way through. And because you have a highest point, you call it the maximum, and that is also your vertex. So the vertex could be the highest or the lowest point, depending on how the graph looks like. Let's take a look at the examples below. Identify the vertex or the middle point of the parabola and determine whether there is a minimum and maximum and what is that point going to be. Let's look at the given. On the first one, the graph opens downwards, so we say, okay, I see. We're going to find the following. We need to identify the vertex. Okay, let's write it down. We're looking for the vertex, and how do we find the vertex? The vertex is the tip of your graph. In this case, represented by this point, which is at 1, 5. That's the vertex. And you said it opens downward. So we have what you call the highest point or a maximum value. The question is, what is that maximum point, right? Maximum meaning you're referring to the y values. What is the maximum y value? Okay, the maximum y value will be at 5. That's how you can tell what the maximum point is. On the other hand, look at this second example. Let's start by identifying the vertex. And yes, you're right, it's actually at negative 2, comma, negative 1, 2, 3, 4, and 5. So negative 5. And because this is the vertex and the parabola opens upward, this time you have what you call the minimum point or the lowest point. Remember, the minimum and maximum points refer to the y values. Now in this case, all the y values are increasing. It just keeps going on infinitely to the positive side. So what would the minimum y value be? Okay, right here. You're right, it is negative 5. And that's how you can tell the minimum and maximum points on a parabola. Let's give you time to practice. At this time, you can pause the video and check your answers afterward. Identify the vertex and tell whether there is a minimum or maximum and where that point might be. On the left-hand side, your graph is opening downward. You have what you call a maximum point, whose vertex is at negative 2, 5. And so we say the maximum point is actually at 5 up here. On the second one, a graph opens upward. And because it opens upward, we say that the vertex is at 3, negative 1. And because, again, it opens up, you have what you call a minimum at the point negative 1 down here, the y values. Okay, so we are able to graph. We're able to tell whether the graph opens up or down. We are able to tell the vertex and whether there is a minimum or maximum point. Hopefully you are going to be able to see this and connect them for the next part. In the next part, we are going to discuss about domain and range. What do you remember about the domain? This was a discussion we had at the beginning of the year. So when you say domain, you actually refer to all the possible x values. What are the possible x values? In the meantime, you have to talk about the y values when you refer to the range. What are the y values in the given graph or function? Okay, so for a quadratic function, unless a specific domain is given, okay, you may assume that the domain is always going to be all real numbers. Okay, remember, unless otherwise stated. So why would it be all real numbers for the domain? Take a look at this example right here. What do you notice about the x values? Does it just stop right here where the arrowhead is at maybe about negative 0.75? No, it doesn't. Because the arrowheads, remember the arrowheads tell you the continuity. It continues on and on. So because of that, we say that it doesn't stop here. Instead, it actually keeps continuing to the left side. And the same thing is happening to the right side. So we say, okay, the domain for this function is all real numbers because there was no specified values for this time, okay? On the other hand, when you talk about the range or the y values, notice how your graph opens upward. So range, we said, are the y values. If it opens up, you have what you call the minimum point. And that's the lowest point, meaning all the y values are actually increasing. And if your y values are increasing, that tells you that y should start at positive 1 right here, the y value starting at 1, and it keeps going on and on and on infinitely. So we say that the range is actually y greater than or equal to 1. Okay, why equal to? Why not just greater than 1? Okay, you're right, because it is a point here and you do include that value because that's where the point actually starts. So let's take a closer look at the example right below. Find the domain and the range. Take a look at the domain. What are the possible x values for the graph? All right, so there was no other statement, so we say, okay, the domain is actually all real numbers. Okay, correct. What about the y values? What are the possible y values so we can identify the range? If the graph opens downward, you have what you call the highest point, and the y values just keep going down, decreasing all the way through. But at what point does that start? What is this location right here? You're right, it's a 4, positive 4. So we say that the range is when the y values are starting at 4, but it keeps decreasing. Okay, so that's how you can tell how to find the domain and the range. So let's give you an opportunity to practice finding the domain and range on the next slide. Okay, you can pause the video at this time. Give yourself some time to answer the question. Find the domain and the range. Okay, let's check. On the left-hand side, the graph is opening up. Because it's opening up, we are looking for specific points to determine the domain and range. Okay, let's start with the domain. There was no specified x value, so we say the domain is all real numbers. It goes on infinitely to the left and to the right. On the other hand, your y values start from negative 4 and keep increasing infinitely. So we say, okay, the range can be represented by y greater than or equal to negative 4. In the same manner, on the second example, this time your graph opens downward. Once again, there was no restriction for the domain, so we say it's all real numbers. Because it goes on infinitely to the left and to the right, this time your y values will start from this point going downward. So what is that point right there? So you count to 4. So we say that the y values are less than or equal to not 3, but 4. Please change that to 4. Okay, so it is actually 4. Okay, so we're overwriting that one. So this is really interesting. I hope we are answering your questions about the quadratic function so far. And please think of questions you might have in mind, list them down, and we can discuss them further. I'll end right here. I'll see you soon. Bye for now.